Welcome to the Mathematics of Juggling. In this video, we're going to answer the question, how many are we juggling, once we know that something is a siteswap. If you haven't watched the video on what a siteswap is, go back, watch that, and then come back and view this video. We showed that 2, 7, 5, 6 was a siteswap. The 2, 7, 5, and 6 represent how long balls will be in the air, those balls thrown at beats 0, 1, 2, and 3, respectively. The beat is simply a time unit. The landing times for the first 4 throws are going to be 2, 8, 7, and 9, which are simply the sum of the values corresponding to the times we throw a ball and then how long they're in the air. So that 8 is the sum of 1 and 7. In order to determine if it was a siteswap, we need to make sure that the remainder we get when we divide each of these numbers by 4 are all different. We use the term mod 4 in that case. We're dividing by 4 because there are 4 numbers in our list. To get those remainders slowly, what we can do is we can draw a little dotted line beneath these landing times, 2, 8, 7, and 9, and subtract 4, provided the number is 4 or larger. We get the differences of 4, 3, and 5. Any of these numbers that are 4 or larger, we subtract 4 from again, and we get 0 and 1 now. And if we look at the numbers at the bottom of each of those columns, we see we get 2, 0, 3, and 1. Those are the values of 2, 8, 7, and 9 mod 4. Because they're all different, it's a siteswap. In order to determine how many balls we're juggling, we're going to focus on the numbers that we find below that dotted line. Here's an example, 1, 4, 1, 4, 5. If we look at the check that we use to see if it's a siteswap, the numbers below the dotted line are 0, 2, and 4. Our landing times are 1, 5, 3, 7, and 9. We subtract 5 from any number that's 5 or larger. We're subtracting 5 because this is a period 5 siteswap. What's special about those highlighted numbers, 0, 2, and 4? Well, we're going to go to the juggling graph to answer that question. Here's our juggling graph, and let's look at the beats 0, 2, and 4. Do you see how those beats are different than the other beats? If not, we're going to do another example. We've got the example of 5, 7, 2, 4, 7. The landing times here are 5, 8, 4, 7, and 11. We subtract 5 from any of those that are 5 or larger, getting 0, 3, 2, and 6. And because 6 is 5 or larger, we subtract 5 from it to get 1. The landing times, mod 5, are 0, 3, 4, 2, and 1. They're all different, so it's a siteswap. Once again, let's focus on the beats corresponding to the highlighted values below the dotted line. That would be at 0, 1, 2, 3, and 6. Do you see how those beats are different than the other beats? In order to really emphasize this, let's blow up 5 and 6. What's different about beat 5 from beat 6? For beat 5, you see we have an edge coming in from the left and an edge going out on the right. That means we have a ball landing at beat 5, and then we're throwing that ball that we just caught. At beat 6, notice that there's no edge coming in from the left, which means we're not catching a ball at beat 6, but we are throwing one. So where does that one come from that we throw? Well, we have to produce it into the pattern. We have to make a new ball for that. So the red dots here each correspond to a beat where we need to introduce a ball, and so that's going to correspond to the number of balls. I've got here a short pattern, 6, 7, 2. I've got 4 copies of it, and we're just going to look at the landing times for it. The landing times for the first 3 throws are 6, 8, and 4. For the next 3 throws, the landing times are 9, 11, and 7, and then 12, 14, and 10, 15, 17, and 13, and we continue to stack those values up. Notice that the numbers in the first column will give a remainder of 0 when we divide by 3. The numbers in the second column will give a remainder of 2 when we divide by 3, and the numbers in the third column will give a remainder of 1 when we divide by 3. In order to check if this is a siteswap, remember what we did was we took the first 3 landing times, the 6, 8, and 4, and we would subtract the period from any of those that were 3 or larger. So we can subtract 3 from 6, 8, and 4 to get 3, 5, and 1. And for 3 and 5, we can subtract 3 from those to get 0 and 2. Here's what's really important. The 3 and the 0, we subtracted a multiple of 3 from 6 to get each of those. 5 and 2, we subtracted a multiple of 3 from 8. And 1, we subtracted a multiple of 3 from 4. So the beats at which we need to introduce new balls are a multiple of 3 less than the landing times of the first 3 throws. In general, if you have a siteswap, the landing times for the first n throws are 0 plus a0, 1 plus a1, out to n minus 1 plus a sub n minus 1. Any beat that's a multiple of n less than these landing times will require a new ball to be added to the pattern. In our first video, we introduced the idea that a letter could be substituted for a two-digit number. A corresponded to 10, B to 11, C to 12, and so on. It turns out that the word theorem is a siteswap. T is a throw of height 29. Out to M is a throw of height 22. The landing times are 29, 18, 16, 27, 31, 19, and 28. This is a period 7 siteswap, so we're going to subtract 7 from these values and continue to do so. All of the numbers below the dotted line will correspond to a new ball that needs to be added to the pattern. Our remainders are 1, 4, 2, 6, 3, 5, and 0. Now we could have obtained these remainders faster by simply dividing 29, 18, 16 by 7. And we'd get those remainders of 1, 4, 2, 6, 3, 5, and 0. The division process, though, produces two numbers. One is the remainder, which we've shown is pretty interesting, but the other is the quotient. Let's look at those quotients. The quotients are 4, 2, 2, 3, 4, 2, and 4. How are those special? Let's look at the number of values below the dotted line in each column. There are 4 below the dotted line in the first column, 2 below the dotted line in the second and third columns. Those correspond precisely to the quotients that we get when we divide the landing times by 7, the period. In the first video, we introduced the mod function. The mod function was the remainder that we got when we divided by n. Now we're going to introduce its companion, the div function. When we divide a by n, the quotient is going to be denoted by a div n. 21 divided by 8 is 2 with some remainder, so 21 div 8 equals 2. 97 divided by 20 is 4 with some remainder, so 97 div 20 equals 4, and 2,294 div 37 will be equal to 62 because 2,294 is 37 times 62 plus 0. Here's our first theorem counting the number of balls. It's called the siteswap div theorem, and it simply says that if you have a siteswap, the number of balls is the landing times div n, the sum of each landing time div n. That's pretty cool. These are the quotients that we get when we divide the landing times by n. Let's check this out with some of our known siteswaps. For 5, 1, we're looking at the landing times, 0 plus 5 and 1 plus 1. That's 5 div 2, which equals 2, and 2 div 2, which equals 1. 2 plus 1 is 3. It's a 3-ball siteswap. For 4, 4, 1, our landing times are 0 plus 4, 1 plus 4, and 2 plus 1. Those will be 4, 5, and 3. 4, 5, and 3 are each equal to 1. The quotients are when we divide by 3, so we get a 3-ball siteswap. And at the end of the first video, I asked the question, how many balls are in the siteswap 5, 2, 4, 5? We look at the landing times, 0 plus 5, 1 plus 2, 2 plus 4, and 3 plus 5. We're going to divide each of those by 4 and look at the quotients, which are 1, 0, 1, and 2 respectively, so it's a 4-ball siteswap. If you know siteswaps, and you've already learned how to calculate the number of balls, you're saying this is not what I learned, because I don't believe this appears in the literature anywhere. What's nice is we can use this to derive the next theorem. We can use the div theorem to derive the next theorem, which is the siteswap average theorem. And if you have a guess, your guess is probably right as to how to calculate it. If you have a siteswap, the number of balls is simply the average of the throw heights. So 5, 1, 5 plus 1 is 6, 6 divided by 2 is equal to 3, 5, 1 is a 3-ball siteswap. 4 plus 1 is 9, divided by 3 is equal to 3. So 4, 4, 1 is a 3-ball siteswap, and 5 plus 2 plus 4 plus 5 divided by 4 equals 4, so 5, 2, 4, 5 is a 4-ball siteswap. Much simpler. At the end of the video, I'll give a proof of the average theorem using the div theorem. So that's really the benefit of the div theorem, is it gives us a nice way to prove the average theorem. The authors in Juggling Drops into Cents, one of the first papers to come out introducing us to the mathematics of juggling, they proved the average theorem in a slightly different way. I like the div proof a little bit better. If you're a curious person, you might be asking this question. Well, hey, let's suppose I have a list of numbers and their average is a whole number. Maybe that would be a way to check to see if it's a siteswap. Unfortunately, that's not the case. We showed in the first video that 4987 is not a site swap, but it turns out that the average of those values is equal to 7. Now, all is not lost. If you have a collection of numbers whose average is equal to a whole number, some arrangement of them will be a site swap. So I have a little puzzle for you. I'll give you the answer to this puzzle before I give the proof of the average theorem. Can you arrange 4, 9, 8, and 7 to form a site swap? There are multiple answers. It's a doable thing. It won't take you too long to find it. To wrap up this video, I want to give one final example just to show all that we've done, and then we'll discuss where we go from there. 557403. It's a site swap. We're going to show it's a site swap, and we're going to determine the number of balls using both the div theorem and the average theorem. To show it's a site swap, we look at the landing times, which are 5, 6, 9, 7, 4, 8, and I'm going to go for the cutthroat method. Just look at the remainders when we divide each of these by the period, which is 6. The remainders are 5, 0, 3, 1, 4, 2. Because they're all different, we can celebrate it's a site swap. The div theorem now is kind of nice after having checked to see if it's a site swap. We have the landing times already listed, 5, 6, 9, 7, 4, 8. All we need to do is take those landing times div 6. So 5 div 6 plus 6 div 6 plus 9 div 6 out to 8 div 6. When we do that, 4 and 5 div 6 will each equal 0. 6, 7, 8, and 9 div 6 will each equal 1, so we get that this is a 4-ball site swap. On the other hand, the quick and dirty method is to just find the average of the throw heights 5, 5, 7, 4, 0, and 3. That average is equal to 4, so once again, it's a 4-ball site swap. No juggling graph required. Oh, where do we go from here? There are actually 2 videos that will be following this one. One is the state of a site swap. The state is sort of like a landing schedule for the balls if we suddenly stopped juggling. It's going to take those numbers below the dotted line and put them to good use. Another video you could watch after this is one about juggling cards. In juggling cards, we're going to dissect the graph into pieces by drawing the juggling graph in a uniform manner. Now, before we get to the proof of the average theorem, we need to answer that question. What arrangement of 4, 9, 8, and 7 is a site swap? Well, it turns out that there are 8 different site swaps that you can come up with. 7, 4, 8, 9, 7, 8, 4, 9, those are site swaps, and then any cyclic shift of them will also be a site swap. So 4, 8, 9, 7, 8, 9, 7, 4, those will be site swaps as well. On to the proof of the average theorem, which will wrap up our video. In checking to see if something is a site swap, we looked at the remainder when we divided by n. In counting the number of balls, we looked at the quotient when we divided by n. So I'm going to introduce variables to represent the quotients and the remainders. Qi is the quotient that we get when we divide the landing time for the ball thrown at beat I by n. And remember that when we add up those quotients, we get the number of balls, so that's really important. Ri is going to be the remainder for the ball, for the landing time of the ball that we throw at beat I. That is, Ri is I plus Ai mod n. In this case, then, the landing time I plus Ai can be written as n times Qi plus Ri. That is, n times Qi plus Ri. And the reason for that is because we're dividing by n, we get that quotient Qi, and then the remainder Ri. To prove the average theorem, we need the sum of the throw heights. Well, the sum of the throw heights, how are we going to get that? Well, they're attached to the I values. So we're going to add up the landing times, 0 plus A0 plus 1 plus A1 out to n minus 1 plus A sub n minus 1. And that's going to be equal to the quotient remainder form of each of those numbers, nq0 plus r0, nq1 plus r1. I want to rearrange these values in a nice fashion. I'm going to put all of the throw heights together, and then I'm going to put all the remainders together on the right side of the equation, together with the quotients in a different set of parentheses with an n factored out. So here we have it so that the throw heights, A0 plus A1, are in one set of parentheses. That leaves the 0 plus 1 out to n minus 1 in another set of parentheses on the left side. On the right side, I've got the remainders grouped together, and then I've got the quotients grouped together with an n factored out because all of the quotients were multiplied by n. The remainders were special because we use those to check to see if it's a site swap. It's a site swap if all of those remainders are different. In order to be different, they have to be the values 0, 1, up to n minus 1, which means that on the left side of the equation, we have 0, the sum from 0 to n minus 1, and on the right side of the equation, the r0 to rn minus 1 will cover all of the values from 0 up to n minus 1 exactly once each. So we could subtract that from both sides, eliminating those terms. Our final step is simply to say, hey, let's take the n that has been factored out and divide both sides by it. On the left side, we have the average of the throw heights, and on the right side, we have the sum of the quotients. But remember, the sum of the quotients is equal to the number of balls. And so that proves the average theorem.